All right, hello, Science 9, Mr. Beeland here. Going to give you your science lesson for today. I am going onto a piece of paper here, and I'm just going to write on here instead. It's just a little bit easier with this section instead of up on the whiteboard. So unfortunately, you're not going to be able to see me, but you can hear me. Okay, so let's get started. Okay, so we have talked about voltage, which is potential energy. We have talked about current, which is the flow of electrons, and we have talked about resistance, and that is the opposition to the flow. So now we're going to put this all together, and we're going to be looking at circuits. Okay, so a circuit is like a complete pathway, similar to like a running track or something like that. And in order for a circuit to work, it has to have, first of all, it has to have a source, right, or a battery or something, and then it has to, connect to something like maybe a light bulb, and then there might be something else, like maybe, who knows, another light bulb. Maybe these are like Christmas lights or something. And then the circuit, just like a track, has to come to a close, right? It has to loop all the way around. So this is called a closed circuit. Sometimes you can have an open circuit, so like when you have a switch and you open it, then the flow can't go all the way through. But right now this is a closed circuit, so our electrons are going to be able to move all the way through. And it's almost kind of like an obstacle course, right? The electrons are going to move down this way, and then they're going to go into the light bulb, and they're going to basically jump through the light bulb, and in doing so, light it up, right? So this particular circuit right here, this is called a series circuit. Okay, so the reason why we call this a series is because each piece comes one after another. So they come in series, right? So first it comes here, then it goes here, then it goes here, then it finishes. And there's only one pathway for the electrons, right? It doesn't have any other choices. It has to go through that way. So the charges, or the electrons, will pass through each of these, and these can be considered loads, right, or your resistors, before they can return back to the end here. So this is a series circuit. Now the other option is, well, what if we split it up? So again, I'm going to draw my battery. I'm going to draw it over here this time, just for convenience. And I'm going to draw it out this way. And then we have a pathway here, and we're going to put one light bulb here. But then we're going to add another pathway right here. And here's a second light bulb. Okay, so here's our two light bulbs. This is still a closed circuit, right? The electrons can move all the way through, no problem. But now when they reach this point here, they're going to have a choice, right? They can go down each side. And they will split up for sure. And this is called a parallel circuit. The reason why we call this a parallel circuit is because once they reach this point, the electrons are going to be able to move down together in parallel. Okay, so again, some are going to go this way, some are going to go that way. And this point right here where they have to make that decision, that's called our junction. Okay, and depending on the resistance of your load, right, so how much resistance each of these light bulbs has will kind of determine how much goes in each direction, right? If this has a very high resistance and it's not going to let very many electrons through, but this one has very low resistance, then most electrons are going to choose to go through this one instead of this one. Now again, this is a parallel circuit, this is a series circuit. One of the interesting things though is, for example, if this light bulb here in the series circuit burns out, right? If it burns out, I'm not actually going to cross it out, but say it burns out. Well, now you don't have a complete loop, right? You would see that we would go here, we would go here, and then it would stop because this is burnt out. So your entire circuit won't work in series if one thing breaks down. I'm going to write that right up here, sorry. Won't work if one component breaks. Okay, so a light bulb won't work. This would be like if your Christmas lights burnt out and one burnt out and then they had to, all the other ones burnt out. And then somebody would have to go through and try and figure out which one burnt out so they can fix it. The nice thing about a parallel circuit is that if, for example, this one burns out, Well, all your electrons can still go this way. So you won't actually have everything shut off. And this is how most Christmas lights work, so that everything runs in parallel, and if something burns out, then your whole string of lights don't get ruined. So there are some pros and cons to each of these series and parallel circuits, okay? So let's have a look here. Okay, let's first talk about our series circuit, right? And the nice thing about a series circuit is that when dealing with the current, so I'm going to write series. I'm going to write current. The current is the same throughout. Okay, so no matter where you check on your series circuit, you're going to have the same current. So again, I'm up here, and if I have 1 amp up here, it's going to be 1 amp here, and it's going to be 1 amp here, and it's going to be 1 amp over here, right? It's all going to be the same. Now, voltage will act a little bit different. Okay, so every device, every load is going to require some potential energy to work, right? And so what we're going to say here is that for the voltage, each load, or each load's voltage adds up to the total voltage. So what does that mean? Well, that means if we've got our battery up here, and let's say our battery is 6 volts, it's a 6-volt battery. And if this light bulb here uses up 4 volts, we have to use up all of the voltage by the time we get to the end, okay? So we have 6, we used up 4, we have 2 left, which means that this light bulb has to use 2 volts, okay? So that's going to be a nice little trick that you're going to be able to find the missing voltages on things, or be able to find the total voltages on things, because the pieces have to add up to the initial amount. Now our last one is resistance, right? So what happens with resistance? So our resistors in series increase total resistance. Which means that your current would go down, right? Because V equals IR, and if you increase your resistance, your amount of current goes down. So this would make sense, right? Because if you have, for example, a flow of water, and you put a small dam or something to block the water, it's going to slow it down. And if you put another block, it's going to slow it down again and again and again, right? So when you put resistors in series, they're going to add up and become more resistant. Okay. All right. So let's talk about parallel now. What happens to current, voltage, and resistance in parallel? Okay. Well, with our current, okay, again, we're going to have that same rule where a current is pretty well going to be equal in most places. However, the current through each pathway adds up to the total. So what does this mean? Well, this means if we look at our current up here, and let's say that we've got maybe, 6 amps going through here. At this point right here, this one, we could even draw a third light bulb. Why not? We've got 3 light bulbs in parallel now. That means that this one here, maybe this one draws 1 amp. This one draws 2 amps. Then that would mean that this last one here would have to draw 3 amps. At the end, once they all come back together, right, they all come back together over here, you'll see that you have 6 amps again. So you have 6 before you go into the junction, 6 after you go out of the junction, but in between they're going to get broken up, okay? So very similar to with looking at these voltages here, your pieces are going to have to add up. So there could be a case where you get asked a question where like something like this is missing and you have to figure out what it is. Okay, now voltage. What happens to voltage in parallel? So voltage in parallel says that the voltage is the same across the loads. So again, if we look up over here at this parallel circuit and say I've got 12 volts here, well, then you're going to have 12 volts on this battery, or sorry, this load, this light bulb, 12 volts on this light bulb, and 12 volts on this light bulb. Okay, so they're always going to be the same in parallel. This means that by the time you go through, you do have all of your 12 volts used up, but basically you don't get to add them up. You don't have 36 volts being used up here. It ends up still just being one set of 12, okay? So finally, what happens with resistance? I'm just going to write R here. So resistors in parallel decrease total resistance. And this is because when you have one resistor in place, that's going to slow the flow down. But as soon as you give that second option, despite it maybe having a little bit of resistance on it as well, now your current or your electrons are going to be able to get to pick which way they want to go, and they're going to pick the easiest way. So it ends up being overall lower in resistance. So that means that as you put things in parallel, your resistance is going to be going a little bit lower, and so your current will actually go up, right? Because there's less resistance to your flow. Okay, so I do want to give you one sample problem about what this would look like, okay? So I'm just going to move this piece of paper, and I apologize for I am using the back of other pieces of paper here just for the sake of not wasting too much paper, so please don't worry about what's going through here. Okay, so if, for example, let's talk about a series circuit, okay? So I've got my series circuit, and I've got one resistor and two resistors, and I say that this here is 20 volts. I've got a 20 volt power supply, and I've got a resistor that's got 5 ohms of resistance here, and I've got a resistor here that's or you know what, I'll change this to 7 ohms of resistance and 3 ohms of resistance, okay? And I know that my I here is going to equal, let's say it equals 4 amps, okay? I don't know what the voltage drop is. I don't know what this I is. And I don't know what this V is. Okay, so let's try and solve this. Okay, so this is a series circuit. So our first rule is current is the same. I got 4 amps here. That means I got 4 amps here. Okay, now we can use, to find V, we can use Ohm's law, right? V equals IR. So V equals current times resistance. Current is 4, resistance is 3. 4 times 3 equals 12. Okay. Now let's look at this one. Again, our resistance is 7 and our current is 4. So we're going to get 28. Apologies. This is 40. Thank you. Sorry. So we should have had 7 ohms of resistance, 3 ohms of resistance, 4 amps going through. So V is going to equal this, okay? Apologies, I was making up the question as I went, and I realized that that number was a little bit off. So again, if our voltage is 40, which it should have been, and our resistances here add up to 3 and 7, right? 3 plus 7 in series, our total resistance, RT, would be 7 plus 3, which equals 10 ohms. And this would make sense because we have 4 amps, 10 ohms, so our total voltage should have been 40, right? And it just gets broken up across these two. Okay, so let's have a look at another quick example here. What could we do here to try and find maybe our initial voltage? Or let's try a parallel one here. Actually, let's try a parallel one. So again, I've got my battery here, and I've got my parallel resistors Okay. Okay, and we're going to say that I've got 12 volts of resistance, or 12 volts here, and we're going to say that I've got, let's say, 2 ohms of resistor here and a 1 ohm resistor here, and I've got, let's say, 6 amps going through this, okay? So, let's find I, and let's find V, and let's find I, and let's find V. Again, I'm kind of making up this question on the spot, so let's hope that it works out. So, our first rule says that for each voltage in parallel, you're going to end up with the same number. So you're going to get 12 volts for both. Now, our question is, what is our current in these cases? So we would just do both of them. I equals V over R. Yeah, I think this one's a little bit off. I think it should be 9. I equals V over R. We're going to confirm that 9 in just a second here. So I equals V over R. We get 12 over 2, which equals 6. So we get 6 amps here. And then same, we're going to do it over here on this one. I'll just write it over here as well. 12 over 1 equals 12. Sorry, I guess that amperage should be a little bit bigger. We don't really know this one for sure until we do all the math, so we'll just double check here in a second. So yes, we have 12 here. So then our total current, it's not going to be 6 or 9, actually. It is going to be these two numbers put together, which is 12 plus 6. So we get 18 amps as our value here. And then that would mean that this one here would also be 18. Again, apologies, I'm trying to make these up as I go, and we're finding afterwards by doing the actual formulas, we're going to get certain numbers instead of just making them up. Okay, so the other thing that we can see here, and this makes sense, right? So this resistor is 1, and this resistor is 2. So this one's half as strong as this one, right? So that means that twice as many electrons would want to go this way because it's easier to go through by a factor of 2. So this is why this makes sense here. This number is twice as big as this number. It means it resists more, so you're going to get about half as many electrons moving through. So the bigger this number is, the smaller this number is going to be, and there is a proportional relationship to them, okay? So again, I was trying to make these up as I went, and obviously there were some things that I had to change just to make it fit. But the questions in the homework are set up. They will work. Yes, I apologize for the long video. This is a lot of drawing and everything and going through problems. But please make sure to sit through the whole thing. If you have any questions, let me know. Okay, take care, everybody.